Hey, Math 30-2s. Using logs to solve exponential equations today. Let's have a look at that. So, quick review. Lesson 1 of this unit, we solved exponential equations involving a common base. So let's do that with these. So I can rewrite 2 to the x equals 32 as 2 to the x equals 2 to the 5th. Now that I've equated these values with the same base, I can equate the exponents. So x should equal 5. Part B, I've got 4 to the x. That can be written as 2 to the 2x equals 2 to the x plus 3. And I can now equate the exponents. So 2x should equal x plus 3. If I minus x from both sides, x would equal 3. All right. So that's a review. We've done that. No issues there. Solving exponential equations by converting to logarithmic form. So consider the exponential equation 2 to the x equals 50. Explain why the solution can't be determined by the above method. Well, 50 is not easily expressed as a power of 2. All right. Determine the two integers between which the solution must lie. Well, we know that 2 to the 5th is 32, and 2 to the 6th is 64. Therefore, x should be greater than 5, but less than 6. Estimate the solution to the nearest tenth. So now you want to grab your calculators and just do a little guess and check. Right, so we want to see what value is closest to 50. So 2 to the 5.5 is about 45.25, and 2 to the 5.6 is about 48.5, and 2 to the exponent 5.7 is 51.98. So to the nearest tenth, the one that's closest should be 5.6. 48.5 is a little bit closer. All right. So we're going to say x should equal approximately 5.6. Great. Now it says the equation 2 to the x equals 50 can be solved by converting to logarithmic form and solving the resulting equation. Complete the work below and determine the exact solution and an approximation of the nearest tenth. All right, so let's do that real quick. So 2 to the x equals 50. Converting to logarithmic form, the log of 50 base 2 is equal to x. And using our change of base, log of 50 divided by the common log of 2 will equal x. So you go to your calculators, figure that out. So part 1, that's an exact solution. Part 2, use your calculators. Go common log 50 divided by common log 2, and we get to the nearest tenth about 5.6. Very nice. Solve the following equations. Expressing the solution as an exact value and to 3 decimals. So step 1, let's rewrite this exponential equation to a logarithmic form. So the log of 7 base 4 should equal x, or common log of 7 divided by the common log of 4 will equal x. So that's an exact solution. Now use your calculators, go common log 7 divided by common log 4, you come up with 1.404 to the nearest 3 decimal places. Part B, in order to solve this equation, I must first subtract 4 from both sides. So 8 to the x equals 36. Again, 36 is not easily put as a power of base 8, so let's write this in logarithmic form. Log of 36 base 8 should equal x. And then as an exact value, using our change of base, common log of 36 divided by the common log of 8. So now use your calculators, come up with this answer to 3 decimal places, and we get x equals 1.723. Right on. Page 284. According to Statistics Canada, In the 21st century, Canada's population has been growing at an average annual rate of 1%. The exponential equation P equals PO times 1.01 to the exponent n can be used to predict the population P in n years after a known population of P to the 0. So if the Canadian population at the beginning of 2001 was about 30 million, estimate the year in which the Canadian population will reach 50 million, assuming the same average annual growth rate. All right, so P is the population that we want to predict, and that's 50 million. So 50 million equals, PO is the known population, well that's 30 million. 1.01 to the exponent n, n is what we're looking for. How many years after 2001? So step 1, divide both sides by 30. And that simplifies down to 5/3 would equal 1.01 to the exponent n. I can now write this in logarithmic form. So in logarithmic form, this is going to be the log of 1.01, no it isn't, the log of 5/3 to the base 1.01 will give us n. So n will be the common log of 5/3 divided by the common log of 1.01. So you go to your calculators, you figure that out. You get 51.337 and so on. What that tells you, it's 51.337 years after 2001. Now, estimate the year in which the Canadian population will reach 50 million. So 51 years after won't quite give us 50 million, so we better say 52 years after 2001, or in 2053. All right. Solving exponential equations using a graphing calculator. So the main objective in this unit is to solve exponential equations using an algebraic technique. A graphical solution can be used to verify the algebraic solution. So back in the previous unit, we used the intersect feature in the graphing calculator to solve problems involving exponential functions. So let's do the intersect method to solve an exponential equation. So it tells us, consider the equation 4 to the x equals 7. Let graph y1 be the left side of the equation, y2 be the right side. So write that down. y1 is going to equal 4 to the exponent x. y2 is going to equal 7. So let's try and graph this on our graphing calculators. Let's go to your y equals screen. If you have anything there, clear them. So in y1 we've got 4 to the exponent x. In y2 we have 7. And let's make sure our window matches what we have in our graph in our notes. So we're told that x goes from about -1 to 4 by a scale of 1. And by looking at that window in our notes, y goes from -7 to 10 by a scale of 1. So now if I hit graph, we'll see 4 to the exponent x and y equals 7. All right, so let's redraw those in our notes. y1 is 4 to the exponent x. There's y1 equals 4 to the x. y2 is 7. We're looking for the point of intersection. So let's go find that in our graphing calculator. And that'll be the solution to this equation. So second, calculate the point of intersection, which is number 5. And we just have to enter 3 times. Find out x is 1.404. So x is 1.404. So, you know, we're a little bit higher than we need to be, but it's all right. All right, on to page 285. Let's solve some exponential equations using logarithms then. Most complicated exponential equations having two variable exponents cannot be solved by simply converting to logarithmic form, although the method of solution still involves logarithms. Big statement here. If two quantities are equal, then the logarithms of the two quantities are also equal. So in this equation, we can solve it by taking the common log of each side and solving the resulting equation for x. Shown below. Complete the work. So the exact solution for 6 to the 3x equals 3 to the 2x minus 1. We're told that if I take the common log of both sides of this equation, I can now solve the equation. And it's still equal. So my rule says I bring the exponent 3x out in front and the exponent 2x minus 1 out in front multiplied by the logarithm. So 3x times log 6, great. Use the distributive property and go 2x times log 3 and negative 1 times log 3. And like we were solving any equation, then I would now get my x's together, so I get a minus 2x log 3 from both sides of this equation. And at this point, the only way to solve for x is to common factor out that x. I'm left with 3 log 6 minus 2 log 3 on the left side. So I want to solve for x now, x being multiplied by 3 log 6 minus 2 log 3. So I want to divide both sides by 3 log 6 minus 2 log 3. All right, so that's the exact value for x. What's the approximation of the nearest tenth? Well, that involves some calculator work. All right, so let's try with our calculators. So my numerator is negative common log of 3. Divide that by, in brackets, my denominator is 3 common log 6, subtract 2 common log 3. And we press enter now, we're going to get the approximate value. It's approximately negative 0.345687124. So this question says the nearest tenth, so that is negative 0.3. Now how do you know if that's correct? The neat thing about a graphing, or this calculator that we have, we can find out if it's correct or not. Let's store this value to x. So hit your store button and hit your x button. Press enter. That value is now stored as x. All right. So if I type in the left side of my original equation, 6 to the exponent 3x, I get a value when x is negative 0.345687124. There's that value for 6 to the 3x. Now if this is a correct value for x, it should equal the right side of the equation, which was 3 to the exponent 2x minus 1. All right, so if we've got the right answer, this should be the same value as 6 to the 3x, or 0.155958626. And yes, it is. We know we've got this answer correct. Beautiful. I've done a check on my calculator. Pretty quick way to do it. All right. Example 4. Use the above method to solve the following two equations and compare the solutions to the review questions at the beginning of this lesson. All right. So we've solved these already. But let's solve them using the method we were told. If 2 to the x equals 32, if 2 to the x equals 32, we were told that as long as those are equal, I can take the common log of both sides and they'll still be equal. So the common log of 2 to the x should equal the common log of 32. And use my laws of logarithms now. Bring the exponent x out in front, multiplied by the log of 2. That should equal the log of 32. Divide both sides by the log of 2, and I get common log 32 divided by common log 2. Well, we can do that in our calculators. If you do that on your calculators, you will find out that x is indeed 5, which was the same answer we had earlier. 2 to the 5th is 32. Let's try the same thing in part B. Take the common log of both sides. So the common log of 4 to the exponent x should equal the common log of 2 to the exponent x plus 3. Our law of logarithms tells us we can bring the exponent out in front, multiply it to the log, so x log 4 should equal x plus 3 times the common log of 2. Now we can't do anything with this x log 4, but I can expand out x plus 3 times log 2. So x times log 2 is x log 2, and 3 times log 2 is a positive 3 log 2. Now I've got my variable x here. I want to get x's together. So in order to get my x's together, I must minus that one from both sides. So I've got x log 4 subtract x log 2 should equal 3 log 2. And if you remember from up above, the only way to simplify this now is to common factor out my variable x. So if I divide x out from both these, I get log 4 subtract log 2. And like we saw earlier now, the way to solve this is to divide both sides by log 4 minus log 2. So I've got 3 log 2 divided by log 4 subtract log 2. All right. Let's use our calculators and see what that gives us. So my numerator is 3 common log 2. Divide that by in brackets, in brackets, log 4 minus log 2. And we come up with an answer of 3, which was the same answer we got earlier. All right. So it works. We are allowed to take the common log of both sides, use our laws of logarithms, and we should get the same answer. Is it easier? No. If you can write this in exponential form and work from there, that's easier. But sometimes we can't do that, as in this question. So example 5 asks us to show the solution to this equation can be written in this form, then evaluate the 2 decimal places. So step 1, let's take the common log of both sides of this equation. The log of 4 to the exponent x plus 2 should equal the common log of 7 to the exponent 2x plus 5. Using our law of logarithms, I'm bringing the exponent out in front. X plus 2 times the log of 4, and same thing on the right side, should equal 2x plus 5 times the log of 7. And I can now use the distributive property, x times log 7 and x times log 4 and 2 times log 4. So x log 4 plus 2 log 4 should equal the same thing on the right side, 2x log 7 plus 5 log 7. And now what I want to do is get my variables together. So let's bring this 2x log 7 to that side, and let's move this 2 log 4 to that side. All right. So I'm going to have x log 4 subtract 2x log 7 equals 5 log 7. That's already there, and I'm going to subtract 2 log 4. And like we did last time, I want to get my x's together. So I want to factor out that variable x. That leaves me log 4 minus 2 log 7 equals 5 log 7, subtract 2 log 4. And then the last step is divide both sides by log 4 minus 2 log 7. So I've got 5 log 7 minus 2 log 4, subtract log 4 minus 2 log 7. And if I look up at the start, that's exactly what we were told to do. Now evaluate this to 2 decimal places. So calculator work. Get out your calculators and type this in. So we have got in our numerator, make sure you put brackets around the numerator, 5 times the common log of 7 minus 2 times the common log of 4. Close the bracket for our numerator. Divide that by our denominator. Start with an open bracket. Common log 4 minus 2 common log 7. And now close the bracket for our denominator. And we'll get this answer to the nearest 3 decimal places. Is that what it says? 2 decimal places, negative 2.78. So x equals negative 2.78. And again, you want to check and see if you got the right answer. We've done this before. Let's store this answer to x. And let's see if we've got the right answer. So the original equation had 4 to the exponent x plus 2. That's the left side of the equation. And the right side of the equation was 7 to the exponent 2x plus 5. Now, if the value we have for x is correct, this should also equal 0.34073100303, and it does. So we now know we've got the right answer. Perfect. All right, so with that quick check. Right on. Let's do the last one, example 6. Note, we can take the logarithm of each side of any exponential equation to any base, but it's simpler to use a calculator base. If the base of the exponential equation is e, then it's simpler to use the natural logarithms, which are of base e, to solve the exponential equation, such as the example below. So let's try this one. So now instead of taking the common log of both sides, we're going to take the natural log of both sides. All right? So step 1, let's get this equation so I've got e to the exponent negative 2x all by itself. So step 1, I'm going to minus 9 from both sides of this equation. So I've got 7e to the negative 2x would equal 12 minus 9, or 3. I'm going to divide both sides by 7. So e to the negative 2x is going to equal 3/7. And the rule now says I could take the common log of both sides, but let's take the natural log of both sides. The natural log of e to the exponent negative 2x would equal the natural log of 3/7. So we know that the natural log of e is 1, so my rule for exponent or for logarithms tells me the natural log of e to the exponent negative 2x is just negative 2x. That should equal the natural log of 3/7. So if I want to solve for x, I'm going to divide both sides by negative 2. So natural log of 3/7 divided by negative 2. So that value to the nearest 3 decimal places. Natural log of 3/7. Divide that by negative 2. And we get 0.4236, so 0.424. Right on. All right, you guys have your assignment. Away you go.